Hello, we're Group 10 and we're going to be presenting our critical design review known as the design and implementations of a wearable haptic glove for immersive virtual reality training simulation. So before diving into the technical details, let me introduce my team. It consists of 2 computer engineers and 2 electrical engineers. Me, I'm Mariana, and I will be focusing on the virtual environment and asset behavior as a computer engineer. We have Daniel Bakos handling the firmware design and asynchronous communication protocols via Bluetooth. And on the hardware side, we have both Brett Labo and William Bland as our electrical engineers, managing the PCB layout, power distribution subsystems, and signal coordinating circuits. And altogether, this is a collaborative split that allows us to tackle our challenge of both hardware and simulation integration. Our main motivation stems from fundamental gap of modern virtual reality. While visual and auditory immersive have reached incredible heights, tactical feedback remains restricted due to basic controller vibrations. And in traditional VR controllers cannot replicate these subtle sensations of grabbing, lifting, holding objects. However, most importantly, by building an adaptive hardware-in-the-loop simulation system, we can capture hand gestures, environmental feedback, and user responses in real time by developing this haptic glove that we'll be introducing to you guys. And this has an immense application potential across high stakes industries such as aerospace, defense, manufacturing, healthcare, where physical muscle memory is very vital. And lastly, our shared passion comes from video games and simulation mechanics that inspired us to develop this project. Our primary objective is to replace physical virtual reality controller inputs entirely with a wireless haptic glove that tracks hand positioning, orientation, and individual finger movements. Technically, this requires mapping clear milestones, and this includes integrating a high refresh rate IMU over I squared C for hand rotation, refining BLE firmware to establish a high throughput, low latency connection with Unreal Engine 5, driving coin vibration motors through transistor-based MOSFET, driver paths to deliver PWM intensity spikes, and of course establishing a custom PCB power subsystem that safely regulates and conditions power distribution for all integrated logic level peripherals.
We selected 3 engineering specifications based on the glove's core functions: power delivery, finger sensing, and haptic feedback. First, we will test 3.3 volt regulation stability to make sure the ESP32, IMU, and sensor circuits receive a stable supply within plus or minus 5%. Second, we will test flex sensor response by bending each sensor and checking that the voltage or ADC value changes consistently while staying within the ESP32 safe range. Third, we will test the coin motor.
Here is our prototype design modeled inside Blender, a 3D application program, and the physical layout is optimized for user ergonomics and structural balance. So we have our flex sensors running along the spine of the fingers to capture accurate anatomical bending angles. And the primary control electronics, which is our custom main PCB, our power regulator board, and the ESP32C3 microcontroller are going to be securely enclosed in a centralized low profile housing mode so that there is no components falling off from the hand, and of course protecting our users from being electrified because safety is our priority. And at the fingertips we have coin type vibration motors are seemingly embedded to apply direct haptic responses to the user's nerve endings the instant a control collision occurs. So anytime a user is close to a virtual object, the coin vibrations will activate.
Here is our hardware block diagram. Our project consists mainboard and regulator board. Mainboard contain microcontroller, which is ESP32, and motor driver for coin-type vibration motor, and unity gain buffer for finger flex sensor. Also, main PCB have 4 individual pin headers connecting to our external peripheral, which is IMU coin-type vibration motor and finger flex sensor. The MCU used built-in Bluetooth module to communicate with Unreal Engine, and Unreal Engine will communicate with VR headset. Finally, the regulator PCB will stack on the main PCB with 5 volts input from power bank to 3.3 volt switching regulator. For the microcontroller, we selected ESP32S3 Room 1 for our project. The MCU have to handle the multiple tasks, measure the finger angle, track the hand motion and send PWM signal to vibration motor as a haptic feedback. It also manages the wireless communication with Unreal Engine. From those specifications, since ESP32 offered both Wi-Fi and Bluetooth communication, high processing capability, dual-core architecture, and more, we decided to use ESP32. For the IMU, we selected BNO055. The main reason we selected BNO055 is this IMU had an additional 3-axis measurement, which is magnetometer. It's measuring the magnetic field of the Earth. The magnetometer solved one of the most challenging problems in motion sensor technology, which is drift. Also, BNO055 offered I2C and UART communication. In this time, we will go with I2C interface. For the finger flex sensor, we selected FLX series, 55mm module used for thumb and 95mm module used for index finger and middle finger. FLX series is offering best specification across the other option. Especially, I think life cycle and flexibility is most important in our project. To provide haptic feedback to the fingertips, we selected NFP Flat C1030 coin-type vibration motor. The ESP32 will send 4 different duty cycles to demonstrate different vibration strengths. And reason we choose NFP flat motor is this motor offered highest vibration force, which is 1.4 G. Therefore, the user can feel enough haptic feedback even using thick glove material. The voltage regulator we decided to use is LM2596 3.3 volt module. While both AP6326 and LM2596 meet our specification, however, since LM2596 series is very popular and widely used step-down regulator in the world, therefore we end up to use LM2596 3.3 volt module.
Next, onto the wired communication protocols, we looked at 3 of the most common wired communication protocols, and ultimately for our project we decided to use I2C for the majority of the components on the board. This is because it offers a good compromise between SPI, having a slightly slower data transfer rate, at the benefits of having a much easier hardware setup, only requiring half as many pins. However, it is much faster than UARTs because it is a synchronous protocol, means it is able to get around the issues of incorrect data sampling and corruption. Ultimately, I2C will be used primarily with the IMU, and the IMU is already designed to work with it, further cementing our choice. Next up, we have the wireless communication protocols, and for these, we ultimately arrived on BLE being the best option. BLE is one of the most power efficient options that we looked at, only being beat by infrared. However, infrared suffers from a very high unreliability with its data. In addition, it has a quite acceptable latency and data rate for our application, and is widely supported by a variety of different devices, which makes it better for the end user as they can use the glove with multiple different kinds of headsets, and easier for development as we can have easier access to documentation and pre-made libraries to aid in the process.
On this slide, we are going to take a look at the hardware design and the overall schematic. Rather than one single block, the schematic is organized by subsystem. The ESP32 is the center of the design. Power enters as 5 volts, the regulator creates the 3.3 volt logic rail, the flex sensors provide analog input, and the MOSFET drivers allow the ESP32 to control the coin vibration motors. The CP2102 circuit gives us USB programming and debugging access. This slide highlights the custom PCB work in our design. Instead of relying on development boards, we integrated key circuits directly onto the PCB, including the CP2102 USB to UART circuit, op-amp flex sensor conditioning circuits, and MOSFET motor driver circuits. These circuits support programming, sensor reading, and pulse width modulation vibration control while meeting the significant PCB design requirement. On this slide, I'm showing the physical PCB layout and the main placement decisions. The ESP32 antenna and USB-A connector were placed near the board edge to improve wireless performance and allow easy laptop access for programming and debugging. The layout was organized by subsystem, including USB to UART, ESP32 control, flex sensor conditioning, motor drivers, and external connectors. Wider traces were used for power and motor paths, while the headers were placed near the edges to simplify wiring to the glove components.
This is our 3.3-volt regulator schematic and PCB layout. Designed for this was referenced from LM2596 datasheet. The female pin header is connecting to main PCB. On the PCB layout, top left corner is 1N5825 Schottky diode. Top center is our LM2596 regulator, and the input capacitor is left-hand side and output capacitor is right-hand side. The 3-amp rated inductor sits right between the two capacitors.
Now into the software design, the overall view of how the system works is as follows. First, we're going to go ahead and calibrate the IMU and finger flex sensors, as these are two sensors that most need a consistent initial state. Then we're going to move on to the process of pairing the controller to the headset and establishing a BLE connection. Once both of these prerequisites are done, we can begin with the operational loop. The operational loop works as follows. First, sensor data from the finger flex sensors and IMU is collected and then filtered. Then the BLE characteristics corresponding to those pieces of data are updated in the headset. Those pieces of information are used to update the position and rotation of the hand, which is then used to calculate collisions and thus used to sent back as vibration commands, which are decoded and then ultimately executed on the board. Next up, we have the IMU software flowchart, and this system is about controlling, communicating, and filtering the data from the IMU. The IMU must be calibrated to ensure the initial position is correct and acceleration vectors and magnetic vectors are properly calibrated. Once that is done, we can send a read request to the IMU via I2C from the board to get that data, and then a Kalman noise filter is applied to reduce the noise as much as possible for dead reckoning. The packet is then sent to Bluetooth, and the characteristic is updated on the headsets to allow it to adjust the rotation and position as needed. However, due to Dead Reckoning's error, it is typically not used for the position, except when camera tracking fails.
So let's take a look at our optical tracking position resolution flowchart. So once connected, the high frequency runtime loop engages, and along the raw analog sensor values are collected and processed through a predictive column noise filter to strip away the jitter and sensor noises. We want everything to be balanced. So this sanitized telemetry is bundled into a compressed data packet and transmitted through Bluetooth characteristics, which leads to Unreal Engine processing this payload to update the virtual hand meshes at real time.
Next up, we have the finger vibration and flex sensors. The first thing we have to do with the finger flex sensors is make sure that they are properly calibrated. This is done because of the fact that different users will have different ranges of motion and thus be able to flex their fingers to different degrees. Once it is calibrated, the ADC can be read and then denoised and used to update the characteristics in BLE on the headset. If it is not connected, it will go ahead and try to send the packets again until it is successful. The coin vibration motors will constantly be waiting for commands to come in from the headset, and once a command comes in, it will be added to a queue, and then when the board is ready, it will go ahead and process that request. In order to ensure safety and proper device functionality without destroying components, there is a safeguard to prevent excessive vibration in the case of a hardware or software glitch. A timer will be started whenever a vibration motor is first activated and will automatically be terminated after a set duration unless another command refreshes that timer.
A critical pivot during our software integration phase involves hand tracking in real time. So while initially we intended to track absolute global positioning using Dead Reckoning from our IMU embedded onto the glove, that can cause a lot of complexity due to limited time. So in order to bypass this, we implemented a tracking source pivot, and we paired the glove with MetaQuest 2's native optical camera arrays to handle all of these transitions smoothly, utilizing our own custom asynchronous C++ Bluetooth Manager plugin for Unreal Engine 5. So this multi-threaded manager processes incoming glove telemetry without interrupting the game thread, preventing a lot of frame rate drops and a lot of glitch. So when the virtual reality hand hits an asset, the Chaos physics engine that is already implemented through Unreal Engine 5 calculates that intersection and sends back haptic intensity adjustments over Bluetooth under a millisecond.
One of the most important things that we wanted to make sure that we were getting working was the Bluetooth communication from the glove to an external device. And in order to do that, we made a small setup, as you can see here, with a finger flex sensor and a coin vibration motor connected to the ESP32. Then we connected the ESP32 with the firmware and then attempted to connect to an external mobile device. Once that was done, the sensor was flexed to see if the readings coming off of the serial output from the ESP32 matched that of the mobile device. And then the mobile device issued commands to activate the finger vibration motor at various intensities. The results from our experimentation was that the serial output from the ESP32 did match that of the mobile output, and that all issued motor commands were successful, and there was a clear increase in intensity from 0 to 100%, indicating that it had gotten the proper readings.
For a haptic glove system, the goal was eliminating the transition delays that break immersion in virtual reality. In order to achieve this, we developed and programmed our own C++ Bluetooth manager. And instead of forcing a slow connection handshake every single time a collision happens, our system establishes and caches the Bluetooth radio connection right at an instant when the game starts. So when you touch an object in virtual reality, an overlap event triggers instantly, sending raw 8-bit byte forms from 0 to 255 straight into our ESP32C3. And this isolates our hardware communication entirely from rendering loop, ensuring immediate physical motor feedback the exact microsecond an interaction occurs. And this can be quite difficult. And we know that our ESP32C3 is communicating with an Unreal Engine. As you see in the log temp group 10, the activation of Bluetooth is complete. And on the bottom image, we see that in real time, we see the tracking coordinations through via Bluetooth, so we know where exactly our hand is in virtual reality.
On this slide, we show the initial testing of the LM2596 voltage regulator board. Since the glove depends on a stable 3.3 volt rail, we tested the regulator before connecting it to the main PCB. For test 1, the regulator was powered from a 5 volt pinch supply with no external load. The output measured approximately 3.26 volts, confirming that it produced the expected 3.3 volt rail. For test 2, we added a resistive load between the 3.3 volt output and ground. The output still measured approximately 3.26 volts, showing that the regulator remains stable under load. Overall, both tests confirm that the regulator successfully converted 5 volts into a usable 3.3 volt supply for the main PCB. On this slide, we evaluated whether the power subsystem delivered the required voltage rails to the main PCB. Before testing sensors, motors, or software, we needed to confirm that the board was receiving stable power. After testing the LM2596 regulator individually, we connected it to the main PCB. The regulator input measured approximately 4.83 volts, and the output measured approximately 3.25 volts, which is within the expected 3.3 volt range. We also checked key component pathways, including the ESP32, IMU header, flex sensor circuit, op-amp supply path, and motor driver circuits. These measurements confirmed that the main PCB was receiving both the 5 volt and 3.3 volt rails needed for continued subsystem testing. On this slide, we are summarizing the successful power testing completed so far. After testing the regulator by itself, We connected it to the main PCB and checked whether the expected voltage rails reached the major circuit areas. The regulator input measured approximately 4.83 volts, and the output measured approximately 3.25 volts, confirming that the 5-volt input was being stepped down to the 3.3 volt logic rail. We then measured key points on the main PCB, including the ESP32, IMU header, flex sensor circuit, and motor driver circuit controls, or motor driver control circuits. Each received approximately 3.25 volts, showing that the 3.3 volt rail was distributed correctly. Overall, this confirmed that the main PCB power pathways are working and that we can move forward with the ESP32 programming and subsystem testing. On this slide, we are showing the main difficulties we ran into during prototype testing and how we addressed them. Our first regulator PCB had footprint issues with the large capacitors and power inductor, and the original inductor traces were too narrow for the expected current path. We corrected this by updating the footprints, widening the power traces, and adding a ground port. The main PCB also initially showed a low resistance short between 5 volt and ground, so we had to troubleshoot before powering it. After the fixes, we verified the regulator output and confirmed that the main PCB distributed both 5 volt and 3.3 volt to key component pathways. The remaining work is USB/CP2102 verification, ESP32 programming, and full sensor and motor testing. This slide summarizes the project budget. We divided the cost into 3 main categories: electronic components, Amazon purchases, and PCB manufacturing. The component cost, including DigiKey and NUARC parts, was about $94.66. Amazon purchases, including the sensors, IMU, power bank, and support parts, totaled approximately $183.38. PCB manufacturing was by far the largest category at $231.65. This is because we had to order multiple board revisions. Overall, the total project cost came to approximately $509.69 so far. This slide focuses on the electrical engineering plan for completing the prototype. So far, we have successfully assembled and tested the voltage regulator board, verified the 3.3 volt output, and confirmed that the main PCB distributes power to key areas like the ESP32, IMU header, flex sensor circuits, and motor driver circuits. The next steps are to verify USB communication through the CP2102 program, and program the ESP32 and begin functional testing. This includes checking flex sensor ADC readings, testing pulse width modulation control of the vibration motors, and verifying IMU communication. After that, the final step is full hardware integration with all glove components connected.